In the earlier lecture, I discussed about the representation of the matrices, and I think you have listened that lecture. So in that lecture, we have discussed an example about the permutation group, and for that particular permutation group, we obtained the representation matrices D is equal to set of set of matrices dx. Now in that example, there were a total 6 group elements. So we can see that the order of the group was 6, and in that example the representative matrices, for example these are the representative matrices. So this matrices was 6 by 6. So you see that in the representative matrices, that means the dimension of the representative matrix and the dimension of the group was same. So that is why we are saying that is whilst a representation obtained in this way necessarily has the same dimension as the order of the group it represents. There are in general square matrices of both smaller and larger dimension that can be used to represent the group. That means it is not always the cases where we will obtain the representative matrix of same dimension as the order of the group. Rather, it may happen that in some cases we may obtain the representative matrices whose order is smaller than the order of the group, and even we can also obtain matrices of some larger dimension. One possibility that arises when the group elements are symmetry operations on an object whose position and orientation can be referred to a space coordinate system is called the natural representation. So again listen the sentences, that is when the group elements are symmetry operation on an object. In our earlier lecture we discussed the symmetry, the group that consists of the symmetry operations on a particular equilateral triangle. So you can also consider that particular group. So when the group elements are symmetry operations on an object whose position and orientation can be referred to a space coordinate system is called a natural representation. So that type of representation will be known as natural representation, and I will discuss about one of such representation. So let us consider another example. Suppose use the fact that the group considered in the previous work example. Previous work example means that in the earlier lecture we took the permutation group and we obtained the representation matrices for that particular permutation group. Now the permutation group that we have discussed is isomorphic to the group of symmetry elements for an equilateral triangle. So the group considered in the previous worked example is isomorphic to the group of two-dimensional symmetry operations on an equilateral triangle. Now for that particular case, that is for the group of two-dimensional symmetry operations on an equilateral triangle, we are going to generate a three-dimensional representation of the group. So our aim is to generate a three-dimensional representation of the group for the two-dimensional symmetry operations on an equilateral triangle. So these operations were already discussed in some of my earlier lectures, but for just for some concept I am again repeating some of the operations. Suppose this is an equilateral triangle and that corners are described by the points P, Q, R. There are three corners for the equilateral triangle and P, Q, R are the respective corners. And for the figure A, figure A, it is the initial figure of the triangle, and we just written 1, 2 and 3, where the position 1 corresponds to the position P, and index 2 corresponds to position Q, and index 3 corresponds to position R. So this is the initial configuration of an equilateral triangle. Now suppose we are considering a particular symmetry operation, which is the operation that is clockwise rotation of 2 pi by 3. Now 2 pi by 3 means 120 degree, and clockwise rotation. So if you rotate the triangle clockwise by 120 degree, then what will happen? So in that case, what will happen? So this particular point 1, this will come to the position of Q. It was already denoted in our earlier discussion, that is this point 1, it will come to the position of Q, that is now 1 will correspond to Q. Previously 1 corresponded to P, but now 1 is corresponding to the point Q. And similarly this position, this 2, that will be shifted to the R. So 2 will correspond to the R and 3 will correspond to the P. So this is the new figure that we are obtaining after the clockwise rotation of 2 pi by 3. Now another operation is the effect of applying a reflection in the mirror axis through Q. So Q is a point. Now you think in this way, that is through Q there is a mirror. The mirror will just run from Q to the midpoint of P and R. So if the mirror is placed in this way, that is Q axis, then what will happen? The point Q, that will remain unchanged, because mirror is placed starting from 2 to the midpoint between P and R, that means in this particular midpoint. So if you place a mirror, 1 and 3 will interchange their positions. Q will remain unchanged, but 1 and 3 will interchange their position. So 3 goes to here, that means 3 is here, and 1 comes to the position of R. So 1 comes to the position of R. So now 1 will correspond to R, 2 will correspond to Q, and 3 will correspond to P. So these are some typical example for the application of the symmetry operations. But we have discussed all types of symmetry operations in some of our earlier lectures. Now suppose we have labeled the 3 corners as 1, 2, 3, and we have placed 3 fixed points in space as P, Q, R, so that initially corner 1 lies at P, 2 lies at Q, and 3 is at the point R. So we take P, Q, R as the components of the basis vector. We know that to find out the representative matrix, we need a basis vector, and in different cases we will take different types of basis vector. So in this particular case, let us take the points P, Q, R as the components of the basis vector. Now the first figure that was I already shown you, that represents the initial configuration. The first figure is the initial configuration, and formally the result of applying the identity I to the triangle. So initial position, I may also call that this is the identity element of the triangle, because it leaves the shape of the triangle unchanged, and it is therefore described by the basis vector P, Q, R, T. T means transpose. So we are taking the basis vector in this way, that is P, Q, R, and basically P, Q, R transpose. Now the second figure that we have shown you, that is the clockwise rotation by 2 pi by 3, and you see it again, that is clockwise rotation by 2 pi by 3. So the new specification is like this. This is the clockwise rotation by 2 pi by 3. So now 1 corresponds to Q, 2 corresponds to R, and 3 corresponds to P, and we can say that this basis vector is Q, R, and P, because 1 corresponds to Q, 2 corresponds to R, and 3 corresponds to P. So we are saying that this basis vector is Q, R, and P. And in the third figure, the basis vector is R, Q, and P. So in this way, we can denote different types of basis vector. So second operation we can denote by QRPT in this way, and for the mirror reflection, the new column matrix, we can say that this is RQPT. So in a similar way, we can calculate different column matrix for different types of operation. For example, suppose for the rotation of 4 pi by 3, and that was actually denoted by the element B. I request the viewers to go through the this particular topic in my earlier lectures, where we have shown the symmetry elements for the symmetry operations for equilateral triangle, and there we have denoted different types of symmetry elements for different types of operations. So the rotation by 4 pi by 3, that is denoted by B, and B can be represented as RPQT. And similarly, we can obtain different types of column matrix for different types of elements. For example, suppose two reflection operations C and D, the column matrices are PRQ and QPR respectively. Now, after obtaining all types of column matrix, we can find the representative matrix M. So for example, suppose the element E corresponds to QPR transpose. So we are writing element E, so this is QPR. Now element E is related to the original basis vector or the column matrix PQR by this matrix, because you see that if you write the matrix in this way, then after multiplication between this matrix and PQR, we will obtain QPR. So you have to find out the matrix elements for the representative matrix, and the process was already described in our earlier lecture, and I think you can find it very easily. So if you place 1 in this position and if you place 0 in all other position, then after multiplication of this matrix with PQR, you will obtain element E, that means Q, P, and R. So naturally the representative matrix D will be transpose of this particular matrix M, because we know that is D is equal to transpose of M. This is actually M. So transpose of M, that will be D. So D E, that is representative matrix corresponding to the element E, is this one, and in prefix we are writing NAT. NAT means natural representation. The definition of the natural representation we have discussed a little bit earlier. So the representative matrix corresponding to the element E is this one. In this way, we can also find the all other representative matrix. For example, DI will be unit matrix. In most of the cases, what we see, that is unit matrix will be the identity matrix. For example, diagonal elements will be 1 and all other elements will be 0. Then E we have just obtained here, and all other matrices can be found by just proceeding in this approach, that is same type of approach. We can find all other matrices. For example, DA is this one, DB is this one, DC is this one, and DD is this one. So we have obtained all 6 representative matrices. It should be emphasized that although the group contains 6 elements, this representation is 3-dimensional. So this is the most important fact here. So please remind that in our earlier lecture we discussed about the representative matrices for the permutation group. In that case, in the permutation group, there were total 6 elements, and the order of the representative matrix for that permutation group is 6 by 6. But here you see that although in the symmetry operation for an equilateral triangle there are total 6 group elements, but the representation matrices which we have found out, you see that the order of the matrix is 3. So this is the difference between this particular example and the example which we discussed in our earlier lecture. Now we will just give the formal definition of the representation. So what is representation? A representation D is equal to set of matrices Dx of a group G is an assignment of a non-singular square n into n matrix Dx to each element x belonging to G. That means for a particular group G, we will obtain a set of matrices or set of representations D, and we are denoting D is equal to Dx in this way, where Dx, what is Dx? Dx is a non-singular n by n square and singular matrix. We have to say this matrix in this way, that is non-singular, not singular. It is a non-singular matrix and square matrix and n by n matrix, n into n matrix Dx to each of the element x belonging to G, such that D of I is equal to In. So what will be the representation matrix for the identity element? That is Di. Di is equal to In. In means the unit n by n matrix. And another property is this, that is dx into dy will be dxy for any two elements x and y belonging to G. If x and y are any two elements belonging to G, and if the product holds in this way, that is x into y is equal to xy, then if we consider the representative matrices, then in that case also dx into dy should be d of xy. That means the matrices multiply in the same way as the group elements they represent. So as mentioned previously, a representation by n into n matrices is said to be an n-dimensional representation of G. So this representation by n into n matrices, we call it an n-dimensional representation of the group G. Here the dimension n is not to be confused with small g, the order of the group. It means that you see that here we are saying that n-dimensional representation, but the dimension small n may be or may not be same with the order of the group, that is small g. N may be same. For example, if we consider the case of permutation matrices, so in that case the order of the representative matrix and the order of the group is same. But later we also discussed the representative matrix for the symmetry elements of equilateral triangle. So in that case we have observed that the order of the representative matrices is less than the order of the group elements. So small g may be equal to small n, or small g may not be equal to small n. A consequence of the two defining condition, these are the two defining conditions for a representation. That means d of I, the representation for the identity element will be a unit n by n matrix. This is the first condition, and the second condition is this, dx into dy is equal to d of xy. Now the consequence is this, the matrix associated with the inverse of x is the inverse of the matrix associated with x. So what is the meaning of this sentence? That I will make it clear. Suppose this is the definition: dx into dy is equal to d of xy. When we are obtaining the representative matrix for the group elements x and y. Now suppose we are assuming that y is equal to x inverse. Now if y is equal to x inverse, and if we put y is equal to x inverse in that particular relation, so we will obtain dx into dx inverse is equal to d of x inverse. That means the right side is d of I, but d of I is equal to in. So if d of I is equal to in, that is unit matrix, then dx into d of x inverse is I, or d of x inverse is equal to dx inverse. So this is the mathematical statement of this sentence, that is matrix associated with the inverse of x is the inverse of the matrix associated with x, and this is the mathematical statement. Now we will consider another example. Suppose we discussed in our earlier lecture about the 4 element abelian group consists of the set 1, I, minus 1 and minus I. So these 4 elements that will constitute a 4 element abelian group, which was discussed in our earlier lectures. Now you take the column matrix, that is we have to take some basis vectors. So the basis vector is the column matrix 1 I transpose. It means that this is actually is U. So we can consider the respective components U1 as 1. So U is equal to 1 I. What is U? U is equal to 1 I. That is the basis vector. And what are the components? It has two components. U1 is equal to 1 and U2 is equal to I. Now if we want to find the representation corresponding to this particular group, then we have to pick elements. Suppose at first we are choosing the element 1. Suppose this is x. So what we do at first, we just check the operation of x on the components of the basis vector. For example, x into u1, it means x is 1, u1 is also 1, so 1 into 1 is equal to 1. That means this is u1 prime. So u1 prime is equal to u1. Similarly, u2 prime will be u2, and naturally the first representative matrix which corresponds to the identity element, that will be a unit matrix 1 0 0 and 1. In the next step, you choose the element x as I. Then you again repeat the process, that is x into u1 will be u1 prime. That means I into u1 is 1, that will again I, so that is u1 prime. Second, that is I means x into u2 means I into I is equal to minus 1. Minus 1 means that is minus of u. So u2 prime is equal to minus u. So from this relation, just if you have understood how to find the representative matrix M, then you can easily calculate the representative matrix at first, that is M. M connects between u prime and u. We know the relation, that is u prime is equal to M into u. So at first you have to find the matrix M, then you can find the representative matrix D as transpose of M. So I hope that this particular discussion you can take as exercise. For example, suppose you have to find the representative matrix D for each of the elements of this particular group, and if you have understood above two examples, then you can easily calculate the representative matrices for each of the elements for this group. So these are the representative matrices for the matrix for the elements of this particular group. For example, this is D of 1, that is representation for the first element. This is d of y, that is for the second element, d of minus 1, that is for the third element, and d of minus I, that is for the fourth element. So these four matrices are the two-dimensional representation for this particular four element abelian group. Now we have also discussed the multiplication table for this four element group, and there we have checked that I into minus I, that will give you as 1. So in the two-dimensional representation, d of I and d of minus I, that will also be d of 1. So if I into minus I is 1, then di and di product d of minus I will also be d of 1. Similarly, if I into I is equal to minus 1, then in the two-dimensional representation, d of I into d of I, that should be d of minus 1. So you can check it that this holds actually. So this is what about the description for two-dimensional representation. Now you may wonder that why anybody would bother with the representative matrices when the original elements are so much simpler to handle. But as we will see later that once some general properties of matrix representations have been established, the analysis of large groups, it may be abelian or non-abelian, can be reduced to routine procedure. So what is our aim? That is, if we use this matrix representation, then analysis of the group becomes very easy and it will be understood in our subsequent lectures. So this is actually what about the representation theory, and I will discuss some more concept of this theory in the upcoming lectures. So I think you have understood about this particular discussion about the representation theory, and for further understanding I request the viewers to go through the textbook Mathematical Methods for Physics and Engineering, written by Riley, Hobson and Benz, and I also thank you all for listening my lecture.